In this lesson, we'll introduce the concept of Bayesian estimation and show how the criteria of minimum mean square error and minimum mean absolute error lead to estimators that are determined by the mean and maximum of the posterior density, respectively. Well, as with our study of least squares and maximum likelihood estimation, let's start with the assumption that we have some parameter A that we'd like to estimate. For least squares and maximum likelihood, we formulated our estimate based on an observation or measurement of data that were related in some way to the parameter. In the absence of measurement or observations, though, we had no way to estimate the parameter. Now let's suppose that, based on our experience or on our understanding of some physical model that relates to the parameter, we have a statistical model that allows us to specify a probability density for the parameter. Perhaps we believe that the parameter has a Gaussian density with some mean and standard deviation, or a uniform density over some interval, or an exponential density with some mean, or a Rayleigh density with some particular mean. Well, in each of these situations, we could make an educated guess or an estimate about the value of the parameter, even in the absence of other measurements or observations. Well, let's call our estimate of the parameter A hat. And based on this estimate, we might define our estimation error as A minus A hat. Then we might associate a cost with this error, such as it's a square, which assigns an ever-increasing cost as the error increases. Or we might define a cost that is uniform, provided that the error exceeds some threshold and is zero otherwise. In the first case, we view large errors much worse than small errors, and in the second case, we view all errors the same, provided they are larger than some acceptable error magnitude. Now, which is best would depend on the particular application and on your preferences and tolerances for error. Now, because we've set up the cost function so that large costs are bad, one way to select the estimate is to minimize the expected value for the cost. That is, we want to make our estimate of the parameter A in a way that makes the average cost the smallest. For the special case of the squared error cost, this expected value looks like this, which we can differentiate with respect to the lowercase a, the value that we're searching over for the optimal solution, which gives us an expression we can set to 0 to find the value that sets that derivative to 0 and minimizes the expected cost. Well, this specifies that our estimate is the integral of the parameter times its density, which is, of course, the expected value for the parameter. This means that the minimum mean square error estimate of the parameter, in the absence of any other observations, is the expected value or mean for the prior density for that parameter. Now let's look at the expected cost for the absolute error. In this case, the cost is equal to 0 if the error is less than delta, and it is equal to 1 if the error is greater than delta. The expected cost then is the integral of the prior density over the region where the error is greater than delta. And this is the same as 1 minus the area of the density when the error is less than or equal to delta, which is 1 minus the integral from the estimate value minus delta to the estimate value plus delta. Now, the optimal estimate for this expected cost is a value for A that minimizes this expression, or the value for A that maximizes this integral. Now, in the important situation where the error threshold delta is sufficiently small, and this would be accomplished by selecting A to be the value that maximizes the prior density. Therefore, the optimal estimate for the average uniform cost is the mode, or the maximum, of the prior density. In summary, then, optimization of the squared error cost results in the mean for the prior density, and optimization of the uniform error cost results in the mode, or the maximum, for the prior density. Now, in some situations, such as a Gaussian prior, those are the same, but in many other situations, they're not. For an exponential random variable, for instance, the mean is specified by the mean parameter, but the mode is always attained at the value 0. Now let's look at the situation when we observe data that are related to the parameter A. A natural extension of our approach then would be to modify the density for the parameter by conditioning on the observed data. Then, by using the same analysis, the optimal estimates would correspond to the mean and the max, but now for the conditional density, f of a given x, or the density for the parameter conditional on the observations. Now we can understand this density better by expanding it with Bayes' rule. One of the terms is the prior density for the parameter, that is, the density that we used before we measure any data. Another term is the density for the observation conditional on the parameter. Now this density is equivalent to the likelihood for maximum likelihood estimation when we treat the parameter as deterministic but unknown, and its specification describes both the deterministic and random manner in which the parameter influences the observation. The last term in the denominator is the unconditional density for the observation, and it is evaluated by integrating the product of the likelihood and prior densities. Therefore, in principle, the posterior density is completely specified by the likelihood and the prior, although evaluating this integral is sometimes a difficult task. Now, in subsequent lessons, we'll address some specific examples of Bayesian estimation, but in closing this lesson, I'd like to point out that the parameter value that maximizes the posterior density can be evaluated without determining the unconditional density for the observation, because the unconditional density for the observation does not depend on the parameter. However, the conditional mean for the posterior will require that we evaluate the unconditional density for the observation. So for some situations, we'll find it much easier to evaluate the maximum of the posterior, or often called the map estimator, than it is to evaluate the conditional mean estimator.